Hi, everyone. I'm Hui Tang. Today, I will talk about my recent work. These are the contents I will present. As we know, the success of deep learning relies on a large amount of training data. Collecting and annotating data for all domains and tasks is extremely expensive. We can tackle it with data-efficient learning, such as semi-supervised learning, SSL. This work falls into the field of SSL. Here is the problem definition of SSL. Given a small labeled set and a large unlabeled set, SSL is to predict class labels for unseen test samples by learning a classification model, which stacks a classifier on top of a feature extractor. Next, I will briefly introduce the related works in SSL literature. Except for those meta-learning-based approaches, existing methods can be divided into three categories: self-training, consistency regularization, and technique combination. For unlabeled data, self-training uses the pseudo-labels predicted by the model itself to supervise the model learning. And a confidence filter is often adopted to select high-confidence samples. Those samples are believed to be the most reliable ones. Consistency regularization enforces the consistency of network predictions between an input sample and its perturbed counterpart. The perturbation lies in input images, output predictions, or model parameters. Recent advances are achieved by technique combination. For example, fix-match is a simple combination of self-training and consistency regularization, which trains the model on the strongly augmented version of a sample with the prediction on its weakly augmented version as the pseudo-label. Recently, flex-match and co-match further improve over fix-match. The selection criteria used in existing methods are usually based on confidence filtering of pseudo-labels, where the unlabeled samples with high confidence remain and others are discarded. We in this work show that the selection criterion can be further improved for better SSL. We summarize our main contributions here. This is the diagram of our method. Inspired by co-training and tri-training, they leverage category predictions of one or two classifiers on unlabeled samples to enlarge the training set. Wherein a designing principle is based on majority voting that shares a similar insight with the popular techniques of ensemble learning. Specifically, we sample multiple classifiers from a learned Gaussian distribution. For the weakly augmented version of any unlabeled sample, we calculate the element-wise product of category predictions from these stochastic classifiers. And select samples with the maximum value in the product higher than a predefined threshold tau. The deep discriminative clustering algorithm can encourage cluster size balance while respecting the underlying data distribution. Thus, we use this algorithm to generate pseudo-labels for unlabeled samples. Specifically, we take an average over the predictions from multiple classifiers and generate pseudo-labels from the thus obtained averages via deep discriminative clustering. Then, with these derived targets, the model is trained using the strongly augmented version of selected samples via a cross-entropy loss. Intuitively, our method shares a similar motivation with these ones based on technique combination, but differs in the aim to progressively improve the noise rate of selected samples by applying the proposed consistency criterion among multiple stochastic classifiers. In a distinctive perspective of designing a more strict filter, which is less explored, we provide theoretical analysis for our method. 3 conditions to progressively improve the model are derived from Theorem 1. Our method can satisfy the 3 conditions, as shown shortly. Next, I will show experimental results. First come the ablation studies. From the figure, we can observe that the aforementioned 3 conditions are better satisfied by our method. As the learning process proceeds, the average variance gradually decreases, suggesting the convergence of the learned Gaussian distribution. The observation can support that the Gaussian in Stocho learning dynamically captures the pattern of sensible decision boundaries. We can observe a clear improvement from the TSNE visualization maps, such as the first row. Our method outperforms or is comparable to the current state-of-the-art on widely used benchmark datasets. All experiments verify the effectiveness of our method. More comparisons and analyses are provided in the supplementary material. That's all. Thank you.